Hooray! Kids, this is going to be a little instructional video on rotational dynamics. So let's, again, as we've done all throughout this unit, let's relate it to what we did first semester, and then we'll talk about this semester and how it relates. So first semester, whenever you're doing dynamics, and it didn't matter what the problem was, what do? Well, you drew your FBD first. So, you know, I don't know, I have a block sliding down an incline, so I draw my FBD. Oops, maybe there's friction, and you get your, and then you would, after you do this, then you would write your equation, or in this case, you'd have to write two equations. Why? Because you have perpendicular, you'd say this minus this equals 0, and then you'd say this minus this, if it's accelerating down, you would say that minus that equals MA. Why? Because when you add all the forces up, you get MA. So F equals MA, okay? So that's the first semester stuff. So in this unit, well, if you have rotational dynamics, this is where you're going to do the same thing. You're going to draw your FBD. Hooray! So let's take, for example, I don't know, I'll set up a couple, but again, I'm not going to solve the problems. If you want to do problems, look at a different video. This is more just conceptually, do you understand what the heck is happening and why we're doing it? So, but our process on how do we go about solving these things, it's the same. So let's say you have a pulley that has mass. Now, first semester we did, hey, you have a massless pulley, you know, but if we have a pulley that actually has some mass, so there's my pulley, okay, and then you say, all right, I'm going to wrap a string around this pulley, you know, like this, and I'm going to have these two massive objects. You know, first semester, this was just, if you like, this was just our Atwood machine, you know, and we'd plug stuff in and solve. Well, guess what? You're gonna do the same things, except, and here's the big except now we have to draw an FBD for this. Why? Because it's gonna rotate. There's gonna be a net torque acting on this. So in this case, if you were doing a problem like this, you would actually have to draw 3 FBDs. That's right. One for this, one for this, one for this. Where first semester, we only had to draw 2. One for this and one for this. Why? Because this was so small, it's massless, it didn't matter, okay? But if that's the case, like, we're gonna have to draw 3 FBDs. So if I draw my 3 FBDs, it would look something like this. You know, if I call this M1 and this M2, so like for M1, you would have force of gravity down, and you would have this force of tension up. We'll say that M2 is more massive than M1, so hey, it's going to accelerate up. So I'd have this bigger FT going up, okay? Well, if I draw, let's draw the FBD for this guy up here. Now this is where you guys have to draw the forces where they're actually applied. Because remember, torques, you got to make like an extended FBD. So if I do that, all right, so this guy, I'm going to have this force of tension going down, which is the same as that force of tension. Newton's third law, action-reaction pair. I'm going to have this, I don't know, some support force or normal force or something going up. It actually would probably be pretty big. And then I would have some force of gravity going down on my pulley. Now these are not going to affect my torque equation because, hey, look, there's my axis, there's no torque with there. But then I'm going to have another force of tension on this side. Okay. Now, let's talk for a second here. Okay. Let's make sure this makes sense. If I say this is more massive, I don't think it's a stretch to go, hey, this guy's going to accelerate down. Well, if this guy accelerates down, this guy's going to accelerate up. Well, if this thing moves without slipping, and it will with these type of problems, that means that this is going to experience an angular acceleration this way. So the angular acceleration for that is going to go that way, or clockwise. Well, that means, so let's just understand, again, understand and apply. Well, that means, wait a second, if my net torque points clockwise, well, that torque has to be bigger than that torque. Well, the only way that that could be is if this force of tension, so I'll call it force of tension 2, is bigger than the force of tension 1. Hopefully, again, that makes sense. And then if you were to write your other FBD, you would have something that looks like this, force of gravity, and then FT2, okay? Where, if you go, well, wait a second, I thought force of tension is always the same. Anytime you're using that always word, I hate that word, because that means you're trying to memorize stuff, not understand stuff. Well, look, this tension is the same as that tension, but this tension is going to be the same as this tension here is going to be the same as that tension, okay? But they have to be different tensions, because if they're not different tensions, I'm not going to have any angular acceleration. And then you would go about just writing your equation. Like in this case, we'd have to write a whole bunch of different equations. For this one, you would say, hey, I would have, if I would write it, might as well write it. For my pulley, I would say, if I call this R, FT2 times R minus, because it's going to, hey, rotate this way versus that way, minus FT1 times R equals, well, what is it going to equal? It's going to equal I alpha, where I would be the rotational inertia of this guy, and then alpha would be my rotational acceleration, so that would be that guy. And then you would have to probably set it up for this, where for this one you might have FT1 minus FG equals MA. Well, wait a second. How does this A relate to this? Hopefully you guys look back at a different instructional video and you remember A equals R times this. If you don't remember that, don't memorize it, understand it. Go back and look at that other video. And then you could, again, do your thing where you have, plug into a system and solve stuff, but conceptually this is going to be what you're going to do. If I wanted to do this guy has to accelerate down. So I would go Fg minus Ft2 equals m2 times A. This would be m1. These A's have to be the same because, again, they're connected by a string, right? And the alphas would have to be the same here and here because it's the same pulley. And then you could plug stuff in and solve. Okay. Just be careful, guys, if you're doing a problem where it's a little bit different. So let's say it was something like this, where you have something rolling down an incline. How would you solve that one? Well, you would do the same steps. You would draw your FBD. Okay, let's draw your FBD. I have the force of gravity acting straight down. Okay. I would have my normal force. Now this is where you guys got to be careful. I'm going to draw them in different colors just so you guys can see that they originate different spots. Normal force starts here and goes that way. Is everybody with me there? Okay, that would be my Fn. And then I would have my force of friction. My force of static friction is going to point this way. And static friction, hopefully you guys understand that. If you don't, you're going to have to look at a different thing to figure that one out. But if you take a look here, okay, this thing is going to be rotating around. There's my axis of rotation. In this problem, Fg does not, okay, Fg does not apply a torque. Why? Because there's no lever arm. Fn does not apply a torque. Why? Because it's not perpendicular to the lever arm. So Ff is the only thing supplying a torque. So if you want something to roll down an incline, you better have friction. If you don't have friction, it's not going to roll. It's going to slide. Again, you would then do your steps. In this case, you would have, hey, I have Ff times my lever arm, which would be the radius of that thing, equals I alpha. And then if you were to write your force equation with the other stuff, you would actually have to write two different force equations. One for your parallel, one for your perpendicular. But your parallel equation would look something like, your parallel equation would be Fg parallel minus the force of friction equals ma. And then this variable and this variable are related, and then you could plug stuff in and solve. But again, basics, okay? Free body diagram. Equation from your free body diagram. Solve. Bye, kids.